All right, last lecture of the unit. We're going to do hybridization. And when I tell you to and what family to do this, you're going to go ahead and be able to complete anything that we did as far as that last column goes on that table. So I hope you all have been working on memorizing that. For Thanksgiving, spend some time. You can even make flashcards or something. I don't know what. If any of you are going on any road trips, you can do flashcards. I bet you there's a lot of online little things you could probably find to quiz you on all this stuff. So actually, that EduWeb Lab has it. You can log in. Do y'all remember the password? Yeah, let's not tell the world what my password is. I'm hoping y'all didn't hear that. But my students know what the password is. So if you log into there, they have exercises, and there's some Vesper drills on there that are pretty fun. So feel free to peruse around that website. No problem doing that. We're going to look at hybridization. And it really looks scary, but it's really not. And it's really simple, and it makes a lot of sense. So we have, let me change my pen color here. All right. When a central atom actually bonds with stuff, the orbitals that it uses for bonding aren't the orbitals it started out with as an atom. Something called hybridization occurs. So I start with the 4 areas because it's the easiest to understand. So if I have an atom here that's got 4 areas around its central atom, it undergoes this particular hybridization. So it's as simple as this. If it has a need for 4 areas of bonding, it needs to utilize 4 of its original orbitals. And we know the orbitals in valence electrons are always the s and the 3 p's, right? That holds those 8 valence electrons. So if we need 4 orbitals, we're going to utilize all 4 of these original orbitals. We need 4 areas. We're going to use all 4 orbitals. And so what ends up happening, imagine throwing these orbitals into a punch bowl, mixing them up, and making 4 brand new orbitals. And that's pretty much what it is. It's truly a hybrid. If this were red and this were blue, those orbitals would be some sort of a purple color, right? Okay, and that's not how it is, but that's just an analogy for you to understand. So what happens, we have a low energy S with 3 high energy P's. We end up making 4 brand new orbitals, all with the name sp3. Do you see where its name comes from? It's made from an S and 3 P's, so we're going to call each orbital sp3. It's not S and P and P and P. This is an sp3 orbital. This is an sp3 orbital. That's sp3. That's sp3. So these orbitals are 109.5 degrees apart, and it's these orbital shapes that dictate our bond angles. Okay? So anytime there's 4 areas, I don't care if it's 4 areas tetrahedral electronically, the hybridization of that atom is sp3. Put it on your table. So next to tetrahedral, trigonal pyramidal, and bent, you're going to write sp3. Tetrahedral, trigonal pyramidal, and bent. That seems pretty simple, right? Yeah? Okay, so let's talk about what about if we have a need to have 3 areas bonded, or 3 areas of density. Well, we're going to use 3 of our original orbitals, and we're going to make 3 new orbitals of average energy, each called sp2, sp2, sp2. That's what these are. sp2, sp2. Those are 3 sp2 orbitals, 120 degrees apart. So my question I ask you is, what is this? What P is it? It's the unhybridized P. This unhybridized P is going to cause us some problems, which we'll talk about in a minute. Okay? But for now, if you have 3 areas, trigonal, planar, or bent, our hybridization is sp2, hybridization. All right, 2 areas. Super simple. We need 2 areas of electron density, so we're going to utilize 2 original orbitals, making sp hybridized orbitals, 2 of them 180 degrees apart. But what do we have here? This guy and this guy. What are those? What are they? These are my 2 unhybridized p's that are hanging out, ready to wreak havoc, ready to wreck shop. Okay? It's these orbitals that are basically the backbone of majority of organic chemistry. It's pretty interesting. So when you get there, you'll understand. You'll understand that. That's why we're still talking about hybridization in organic. And I still have to ask them these questions, and they act like they've never seen it before. And I'm like, no, I did it just like I'm doing it now. I did it with them. Okay. So if there's 2 areas, linear, what's my hybridization? SP. So go ahead and put that on your chart. Now, there's nothing drawn for 5 or 6 areas just because it's impossible to draw easily. So let's just talk about it. For 5 areas, I'm going to use an S, a P, and a P. Uh-oh, now what am I going to use? I'm going to expand the valence and use a D. So I end up with 5 orbitals, each with the name sp3d. So areas, the 5 areas, trigonal bipyramidal, seesaw, T-shaped, linear, sp3d. So you guys follow patterns. What would the octahedral family be? Yep, sp3d2. And that's why only certain elements can expand their octet. They have to have those d orbitals available to throw into this hybrid in order to make those extra orbital availabilities. Okay, so now we're going to move on and talk about sigma and pi bonds. A lot of teachers just tell their students, okay, folks, I want you to memorize this. If you have a Lewis structure and you see a single bond, that counts as a sigma. And if you have a double bond, it counts as a sigma and a pi, and a triple bond is a sigma and a pi and a pi. And at the end of the day, yes, this is what you need to memorize. But I don't like you just memorizing stuff without understanding it. So I'm going to go into a really detailed explanation about this. But this is referring to Lewis structures that you draw, Lewis dot structures. And if I ask you how many sigmas and pi's there are, you need to be able to do that. A single bond is a sigma, a double bond is a sigma and a pi, and a triple bond is a sigma and a pi and a pi. Okay? Now, let's talk about the characteristics of sigma bonds. Sigma bonds are single bonds. You've seen them in molecule kits. When you make a single bond, free rotation, what does that mean? That means I can rotate any of these atoms. That's what single bonds allow, okay? And they're characterized by head-to-head overlap. What that means is when 2 orbitals are hanging out next to each other and they just go like this and bond that way, that's considered to be a sigma bond, okay? And then finally, oh yeah, and it's also part of double and triple bonds, which we'll talk about when I draw pictures. Now, pi bonds, these are what we find in double or triple bonds. Notice, you know that with double and triple bonds, we talked about length and strength, right? Which ones are stronger, double or triple? Triple. Which ones are shortest? Triple. But notice I can't rotate around them. No rotation. So that's what no rotation means. What makes double and triple bonds are these unhybridized P's that we were talking about before. Unhybridized P's. And I'm going to actually show you this. But every double bond has 1 sigma, and then 1 pi is a double bond, and then a triple bond is 1 sigma and 2 pi. And what I'm going to explain to you is where that comes from. So is everyone with me so far? All right. So this is the part where if you just want to listen, you can listen. I suggest you draw, but it's up to you. So I am going to draw the Lewis structure of ethane. Ethane has 2 carbons and is fully saturated with hydrogens. So single bonds for carbons, and then I've got all these hydrogens single bond. So when I draw, I'm going to kind of draw the hybridization of this so you can see it. First thing I want you to do is look at that one carbon. How many areas are around both the carbons, actually? 4 areas. So what's the hybridization of both of those carbons? sp3. So we know that both of these are sp3 hybridized. So what happens, we have a carbon here, and it's going to have 4 sp3 orbitals 109.5 degrees apart. Okay? Each one of these is called sp3. That's crucial for you to remember that, because that's the hybridization. So what's going on with this other carbon? How many orbitals? It's the same. It's got 4 sp3. Here's where we get our first sigma bond. Bam! 1 sp3 overlaps with that sp3, and that is the bond that exists between those two carbons. It's an overlap of their sp3 hybrid orbitals. All right. So far we have 1 sigma bond right here. So where do the other the single bonds come from, the other sigma bonds? That's from the hydrogens, right? Hydrogen is a peripheral atom. It only has 1 orbital available to itself, which is the s orbital. Can you mix the one s orbital and make something new if you only have one thing? Can you get a hybrid? No. So what you actually have overlapping with every single one of these is the s orbital from the hydrogens. It's a head-to-head overlap, so all of these are sigma bonds. So anytime you see a single bond in a Lewis dot structure, it is a sigma bond. So how many sigma bonds in this picture? 7 sigma bonds. So one of the sigma bonds is an sp3 overlap. All the other sigma bonds are S overlapping with sp3. Okay? All right, now let's talk about ethene. Let's crank it up. Ethene has a double bond in it, leaving me with 2 H's on each. This is where everything comes together as far as this stuff goes. So what is the hybridization around each carbon? 1, 2, 3. What's the hybridization? sp2. So if I have sp2 hybridized orbitals, it means I have 3 orbitals that are 120 degrees apart from each other, each of them called sp2. sp2, sp2. But what else does this carbon have? Yep, remember this carbon has an unhybridized p? You remember? Because we only use 2 of the 3 p's? It's kind of chilling right there. So what is it going to do? Well, let's draw my other carbon in here. This carbon has an sp2 overlap. This is why a double bond has a sigma bond as well as a pi. It's the sp2 hybrid orbital overlap that is our first single bond here. Let's talk about our other single bonds. Oh, wait, let me draw. What else do we have on this guy? Another unhybridized p. So our hydrogens are going to overlap, our s orbitals from the hydrogens are going to overlap here. So that's another 4 sigma bonds. So what do these p's do? These p's will sideways overlap. They literally do this. The feet and the hands, they go to the side, like a crescent moon. So what happens, this thing overlaps, this one overlaps, and they make this donut-y looking shape. That is 1 pi bond. So a sigma and a pi make up a double bond. What does it look like? Well, here's I had to get these from the UK in order. I didn't go to the UK to get them. I ordered them. But this is ethane. You can see the single rotation, and then I'm going to pass along with it ethene. I know this looks like a triple bond, but it's not. This is only one unhybridized P overlapping with one unhybridized P sideways. Because it's this sideways overlap thing, that's what defines the pi. Okay? So this is a double bond, and there's single bond. And notice there is a sigma and a pi in every double bond. So you can look at them and pass them around. All right, let's move on to the next. And that's going to be ethine. What does ethine have? A triple bond. So that gives me 1H, right? So what's my hybridization around each C? sp. So I'm going to have a C and a C with sp hybridization, where these things are 180 degrees from each other. So this is sp, this is sp, this is sp, and this is sp. Okay? But what do each of these have, each C have in addition to that? 2 unhybridized P's. So it's got one going up and down like this, and technically the other one is supposed to be coming straight out at you. But I can't draw that, so I'm just going to draw it like at an angle. Okay? So these are going to overlap. The greens are going to overlap here and here, and those are coming out like a disc, like that. And the other ones are 90 degrees from that. The reds. There's going to overlap, and this is going to overlap. This is really hard to see. I've got a model for it. But what else do we have? We got some more sigma bonds to take into account. We're not done with our picture. Yeah, our s orbitals for the hydrogens are going to head-to-head sigma bond overlap with. So this triple bond is made up of 1 sigma and 2 pi bonds. This is what it looks like. It's nuts. So we got the overlap this way, making the 1 pi bond, and the overlap this way. What makes these so important in organic chemistry is these are the electrons that are just basically out and naked to the universe, ready to react. So when any electronegative element comes in, or something with a high electrophile that loves electrons, it'll grab from here. It's easy to grab from here. And that's where we get our mechanisms and the basis of everything we do in organic. So go ahead and pass that around. So that kind of makes sense? Maybe? Y'all are too quiet. All right, so we're going to look at this. I'm going to redraw this structure just because it throws people off. So notice this N has got 2 H's on it, so I'm going to redraw that. I'm going to include every lone pair I see. And I am skipping some pages, it's fine. We're going to get enough practice. Okay, so that's the structure we're looking at. All right, what's the bond angle around each of the 2 carbon atoms in the hybridization? So starting with this carbon atom here, what are the bond angles? First thing, how many areas? 4. So what are the bond angles? 4 areas that are all bonded. What are 9.5? And what's the hybridization of that? sp3. Good. What about this carbon? How many areas? 3 areas. What's the bond angle? 120. And then the hybridization? sp2. All right. What are the hybridizations of the orbitals around on the 2 oxygens and then the nitrogen? So I'm going to do the nitrogen here. What is the bond angles? How many areas first? 4 areas. So what's the bond angle? It's less than 109.5 because of that lone pair. It's about 107-ish. And what's the hybridization? It's still 3 areas, regardless of how many of them are bonded or not. And then this oxygen up here. Don't worry about the bond angle's weird because it's only one thing attached to one other thing, so it's always 180 to the thing below it. It doesn't really follow the rules, so the bond angle is weird. But you can tell me the hybridization. How many areas around that oxygen? 3, so it's sp2. And then our last oxygen here, bond angle? No, that's because it's drawn that way. You can't do that. You can't get in that trap. It's got 4 areas, 2 of them bonds, 2 lone pairs, so it's not 109.5. It's not 107. It's about 104. Less than less than. It's about 104. And then what is the? And it is bent. The fact that I'm drawing it straight doesn't mean anything. Okay, it is bent there, and it's just not drawn that way in a 2-dimensional situation. What is the hybridization? sp3. All right. Part C. What is the total number of sigma bonds in the entire molecule and pi bonds? So, because this is video, I'll count with everybody. So I'll change the color to yellow. 1, 2, 3, 4, 5, 6, 7, 8. What about that double? One of them is a sigma, so that makes 9 sigma bonds. All right, and then what about the pi's? How many, do I have any pi's here? 1, because of the 1 overlap of the unhybridized orbitals on that double bond. 1 pi. So sigma can be written with a lowercase s like that, and pi can be written just like you've always written pi. That looks weird. I can't do it. It's like that. It's like a standard deviation symbol. Uppercase sigma is that. Right? This is a lowercase sigma. Okay, we're going to do the same thing just with this last one for practice, and then we're going to be done. I'm going to let you start your homework. Okay. All right. For this first carbon, bond angle. Hybridization. Because we said that was 4 areas, right? This carbon. 3 areas. Bond angle. Hybridization. sp2. This carbon. Bond angle. Hybridization. Little nitrogen, our friend. Bond angle. It's about 107. And then hybridization. sp3, still based on total number of areas. All right, and that is hybridization in a nutshell. We are not doing molecular orbital theory this year, so the rest of the notes, please don't study, unless you just want to. I'll happily explain it after you study it on your own. More than happy to do that, but we're not teaching it. So go ahead and start your homework. And notice there's a note that says any molecular orbital theory questions in the homework key you don't have to do. It mentions that in the actual homework, okay? Not in the book, in the newest homework online. All right, that is all.